Hello, Algebra 1 CP students. Hopefully you're having a fantastic day so far. Today, I would like to continue our discussion on solving systems of linear equations by substitution. I'd like to show you two more regular examples, just like we talked about in class yesterday, and introduce you to special cases. Just like we saw with graphing, how we can get no solution if lines are parallel, or infinite solutions if the lines overlapped. The same type of thing can happen with substitution, of course, because we're still solving systems of linear equations. So I'll show you an example of no solution and an example of infinitely many solutions. But before we get to those, I would very much like for you to try this problem on your own based on what we did yesterday. Use your notes from yesterday's class to solve the following system of equations by substitution. That means we're trying to get a value for x and a value for y that make this equation, both equations, true simultaneously, right? That make this system true. Pause the video, take about 5 minutes, see if you can solve this on your own, and then we'll pick back up in about 5 minutes. All right, by now I assume that you've paused the video, tried this problem on your own. Hopefully you were able to get an answer. If not, maybe you got stuck somewhere. Hopefully you were at least able to get a starting point. What we do at the very start of this is I kind of look at my problem and I say, I need to isolate one of those variables. I don't have a nice thing that says x equals this value or y equals this value right from the get-go. So I need to do a little bit of algebra to make that happen. Which one of these looks like it's going to be pretty easy to isolate? Well, this one. Notice if I had to do a little bit of algebra to get this x by itself, all I'd have to do is just add 7y to both sides. And that's it. We'd have x equals 23 plus 7y with no fractions or decimals unnecessarily. Right? See, it wouldn't make sense to try to get y by itself, because then I would subtract x from both sides, so we'd get 23 minus 7x, and then divide both sides by negative 7, we'd get unnecessary fractions and decimals. It's all about trying to find that easy starting spot. Okay, so here I would choose, and there may be more than one, like getting the 2x by itself might not be bad either. Add 4y to both sides, divide everything by 2, it divides evenly, so that might work out in your favor as well. But I would choose, I see the coefficient of 1, so I would choose the top. And I'd say, well, if I add 7y to both sides, that would give us x is equal to 23 plus 7y. And now if we know that x is equal to 23 plus 7y, we now have a new name for x. We're going to call it 23 plus 7y. We can substitute that 23 plus 7y in for this x in the equation we've yet to touch. It always goes into the other equation. Because we've worked with this equation already, we used our top equation to get this. We can now take this and put it into our second equation. All right? Because if we know that x is equal to 23 plus 7y and 2x minus 4y equals 6, then we know that 2 times x, which is 23 plus 7y, minus 4y should equal 6. Okay? Hopefully in doing this problem yourself, you were able to get this far. But if not, hopefully it makes sense as to how we got here, right? Again, we're just replacing the value for x with 23 plus 7y, which is what we got. And notice I'm using those parentheses because I do need to make sure I distribute that 2 to everything. Always use parentheses when you substitute like that. Solving this equation now, this is just like an equation we did in like September and October of this year. We would say 2 times 23, that's 46, plus 2 times 7y, 14y, minus 4y is equal to 6. 14y minus 4y, let's say 46 plus 10y is equal to 6, right? Combining like terms. Now we have a two-step equation, which we love. Isolating y, we would subtract 46 from both sides. We'd get 10y is equal to negative 40. And lastly, we could divide both sides by 10 to undo that multiplication of 10 times y and get y is equal to negative 4. Again, hopefully you're able to do that on your own since I asked you to try it as a do now. But even if not, hopefully it now makes sense as to how that was done. Okay? We're not quite done with our problem yet, though. Remember, this is really only halfway there. The other half is now figuring out what x is. Now that we know what y is, let's use this information to solve for x and say, well, we set up at the top that x was equal to 23 plus 7y. If y is negative 4, then that means x is really 23 times plus 7 times negative 4. Because y is negative 4. Which means that x is equal to 23 minus 28, or in other words, negative 5. So the solution to my system of equations would be that x is equal to negative 5 and y is equal to negative 4, which you could certainly write like that if you wanted to, or you could write it as an ordered pair to say the solution is negative 5 comma negative 4. Here's my x, here's my y. All right, and that's exactly how it's done. Hopefully that made sense. Hopefully that's what you got when you did it on your own. If not, hopefully you realize where you may have made a mistake. Something else that I want to bring up is the fact that you can check your work using these values. I just said at the beginning that we're trying to find a value for x and a value for y that satisfy both of these equations simultaneously. So that means if I plug this in for x and I plug this in for y, it should make this equation true. Does it? Well, it takes only a couple seconds to find out. If x is negative 5 and y is negative 4, is it true that negative 5 and then negative 7 times negative 4 is going to be positive 28? Negative 5 plus 28 is equal to 23? It is. Is it true that 2 times negative 5, negative 10, minus 4 times negative 4, so plus 16, is equal to 6? Negative 10 plus 16 is equal to 6. So it works. So that's a great way on any sort of assessment or just practice work that you're doing to check your work. It only takes a couple seconds to do so, and it's well worth it, I think, especially when you're just starting out. All right, let's do another one kind of like that. We have something like this. Ready? How about negative 5x plus 7y is equal to negative 5? And then negative 3x plus 6y is equal to negative 12. Again, the challenge here is kind of figuring out where to start, right? I want to look and see, which variable would be easy to isolate? Think about it. It wouldn't really make sense to isolate the 7y, for example, because if I added 5x over to this side, we'd get 7y is equal to negative 5 plus 5x. And then dividing everything by 7, we would get a lot of ugly fractions and decimals. Ugh. Let's try to avoid that if possible. Same thing if I tried to move the 5x over. Or, sorry, tried to move the 7y over. We would eventually get 5 divided by 5 would work, but 7 divided by 5, unnecessary fractions and decimals. We don't like them. The second equation, though, is a little better, particularly in trying to isolate x. Right? Notice, if I were to isolate x, that means I would subtract 6y from both sides. We'd get negative 12 minus 6y. And then dividing everything by negative 3, that would work out evenly without any fractions and decimals. That would be great. All right? So that's exactly what I'm going to do for this second equation. I'm going to say, let's take this second equation and manipulate it to solve for x. In doing so, we can subtract 6y over to the other side. Gives us negative 3x is equal to negative 12 minus 6y. And now I can divide everything by negative 3, giving us that x should equal negative 12 divided by negative 3, positive 4, plus 2y. Notice, no unnecessary fractions and decimals. We're not making it harder on ourselves for no reason. That's a nice expression that we could then substitute for the x in the first equation. All right? But it's a little bit of logical thinking. That's why it's tough. I try to explain my thought process as clearly as possible because it's really exactly that. It's a thought process of saying, which one of these is going to be easiest to isolate? And it's going to just depend on the problem. It's going to depend on the problem. But now that I have an expression for x, we could take that expression for x. If x equals 4 plus 2y, we can use that knowledge up here to substitute for this x. Right? If we know x is equal to 4 plus 2y, well then in our first equation, we'd be able to say that negative 5 times x, which is now 4 plus 2y, plus 7y is equal to negative 5. All right, hopefully that makes sense as to how we proceeded there. Going forward, we could say, well, let's distribute. This is now, I think this is the easy part at this point. This was the hard logical thinking new part. This is going back to solving equations, solving linear equations. We did that with one equation, one variable. We can distribute. We would get negative 20 minus 10y plus 7y is equal to negative 5. Combining like terms would now tell us that negative 20, let's see, minus 3y is equal to negative 5. We can add 20 to both sides to isolate y, giving us negative 3y is equal to negative 15. Oh, sorry, positive 15, my fault, positive 15. Negative 5 plus 20. I was going a little too fast there. Negative 5 plus 20, positive 15, not negative. And lastly, divide both sides by negative 3. We would get that y is equal to positive 5. Oh, jeepers, it's not. Y is equal to negative 5. Oh my gosh, I'm getting my negatives and positives mixed up. Ugh, I have too many things on my mind. I'm trying to pace myself for the next question. Let me just slow it down. I would say add 20 on both sides. Negative 3y is equal to positive 15. Divide both sides by negative 3. We get y is equal to negative 5. That's positive 15 divided by negative 3. Jeepers, that's embarrassing. Holy cow. But hopefully that makes sense. All right. Now that we know that y is equal to negative 5, we can use that information right up there to say, well, if y is equal to negative 5, then that means that x is equal to 4 plus 2 times negative 5. So x would therefore be equal to 4 minus 10, which is negative 6. And so we'd see the solution to my system is x is negative 6 and y is negative 5. Or you could write it as an ordered pair of negative 6 comma negative 5. All right. Sorry about the little mix-up with the positives and negatives there, but hopefully that makes sense. Okay, how we isolate the variable. We kind of discover which one is easiest to isolate, which I guess at a worst case could be a process of elimination. You only have 4 variables, first x, first y, second x, second y. One of them is going to work out nicely. So maybe it's a process of elimination at worst case, but you should be able to use a little bit of logical thinking to figure out which one's going to work best. Once you do, take that and substitute into the equation that you have yet to touch. Solve just like we did before, one step, or not one step, but one variable equations, linear equations like we did in September. And then use this information to solve for the other variable. All right. Now, while we have time, I want to show you some special cases of this type of stuff, namely problems in which we get solutions of all real numbers and problems in which we get no solution. Actually, I shouldn't say all real numbers. I should say it's a solution of infinitely many solutions. It's not all real numbers. Not any number in the world will work, but there are infinite possibilities of pairs that will end up working out. Okay, so I shouldn't say all real numbers. I should say it's either infinitely many solutions or no solution. Let's take a look at those special cases now. Okay, starting with infinitely many solutions. Let's consider a problem like this. If I had negative 4x minus 4y is equal to negative 16, and I also had negative 12x minus 12y is equal to negative 48. Just like when I was graphing lines, one thing that you may notice in these equations is that they're essentially multiples of each other. If you took the whole top equation and multiplied everything by 3, you would end up with the bottom equation if you tripled everything in that top equation. That's already a good indication that something fishy is kind of going on here. But in case you didn't see that and tried to solve it normally, take a look at how this would play out. Both of these equations have great starting spots for everything. Everything's going to divide evenly, which I really like. So suppose we just decided to isolate y on this first thing. Okay? In order to accomplish that, we would manipulate this top equation by adding 4x to both sides in order to move it over to the right. That would give us that negative 4y is equal to negative 16 plus 4x. We would then divide both sides by negative 4, divide everything by negative 4 to get y alone, and we'd say that y is equal to negative 16 divided by negative 4, positive 4, negative 4 divided by, positive 4 divided by negative 4, negative 1x. We'd see y is equal to 4 minus x. Sure, seems like a regular problem so far. Let's take this, now that we know this, and plug it in for our y right here. Right? We're just going to take that y and put it right in for that y. And say, well, that means that negative 12x minus 12 times y, which we're now going to call 4 minus x, should equal negative 48. Well, this is our one equation, one variable. Let's try to solve it. I would say here we can say negative 12x. Let's distribute. Negative 12 times 4 minus 48. Negative 12 times negative x. Positive 12x plus 12x is equal to negative 48. And something very weird happens when we combine like terms. Negative 12x plus 12x goes away because that would just be 0 x's. If I have negative 12 x's and then add 12 x's, we now have no x's left. And we get negative 48 is equal to negative 48, which is a true statement. This is bringing back all sorts of memories from when we saw this when we solved equations. When we solved equations and we ended up with a true statement, we were able to say that that equation has a solution of all real numbers. Pretty much the same thing is going on here. If I'm solving a system of equations and I notice that along the way when I solve by substitution, I end up with a true statement, all my x's cancel out and everything's true, then we would say that this system of equations has an infinite number of solutions. Because the idea is no matter what value you picked for x, this would equal this. And no matter what value you pick for y, as long as it's paired up with the x, this side would equal this side. It's an infinite number of solutions. Okay, because it just results in a true statement all the time. All right. You could write that by saying it's an infinite number of solutions, or you could use the shorthand of infinity, which I see a lot. Okay, I don't know if that's technically proper, but I do see it a lot, even in textbooks, so that's totally fine. All right. Just like how we can get an infinite number of solutions if we end up with a true equation, a true statement, which is what we saw like way back in October, if you remember, we can end up with no solution if we see a false statement. So let's take a look at an example that would make that happen. Consider this. 3x plus 3y is equal to negative 4. So here again, we see a true statement all the time, meaning it's an infinite number of solutions. How about this? 3x plus 3y equals negative 4, or the opposite of x minus y is equal to negative 7. Well, this is a nice easy thing to work with down here. This up here, we're going to get fractions and decimals. So let's try to manipulate the bottom equation. Suppose we want to get x by itself. I would accomplish that by adding y over to the other side. So I would get the opposite of x is equal to negative 7 plus y. I could now divide everything by negative 1 to undo that negative 1 times x and get x is equal to positive 7 minus y. Okay, great. X is equal to 7 minus y. Let's take that value for x and substitute it into my first equation for x, right? Just like we've seen all along. Take that value and just throw it right up there. We would get now that 3 times x, which is 7 minus y, plus 3y is equal to negative 4. Doesn't seem too weird so far. Let's distribute and see what we can do. We're going to get 3 times 7 is 21 minus 3 times y minus 3y plus 3y is equal to negative 4. And now you might start to see the weirdness showing up. Look what happens again when we combine like terms. Negative 3y, positive 3y, that's 0y. All the y's go away. And we're left with 21 is equal to negative 4, which unlike before, which was a true statement, meaning that no matter what value you pick, you're going to be happy. Here, no matter what value you pick, you're going to be unhappy. And so this was a true statement, had infinite solutions. This is a false statement. 21 is not equal to negative 4. So that means there isn't any value for y that could work here. And therefore, we would say that this system of equations has no solution. Which again, you could write out the words no solution, or you could use that notation. So just like when we solved regular old equations way back in the day, it's like good times, back in October, when we saw that the equations resulted in a true statement, all those variables canceled out and there was a true statement left over, we could say that there's an infinite number of solutions. If all the variables cancel out and there's a false statement left over, then there's no solution. That can happen in systems as well. It happens all the time. You saw it in graphing. Infinite solutions would overlap. No solution would be parallel lines. Here, this is what that looks like algebraically. Still working with systems, just now the algebra side versus the visual side. All right? So, sorry, I know that was a little long-winded, but I just wanted to try to be as clear as possible. Just to give you a recap of what we did today, we solved two systems of linear equations by substitution on the front side here. We had to isolate one of the variables, substitute it in, solve, take that information, plug it back into the top, and figure out the last piece. Same thing for the second one, where we had to do a little bit of thinking to figure out which one of these is going to work nicely to isolate, but we were able to accomplish that. And then on the back side here, we took a look at two problems that were special cases. One that had an infinite number of solutions, and one that had no solution. All right? Thank you so much for your attention and focus today. Please try those practice problems on your own if you get a chance. They're on Google Classroom. We will practice this on Thursday and Friday as well. So it's important that you understand this because I think this is like one of the crucial ideas of Algebra 1. All right, so please make sure you do your very best. Thank you so much and have a fantastic rest of your day.